Good morning, everyone. So this week we're going to wrap up regression. Today we're going to wrap up one variable regression, and then we're going to go on to look at what if we want to predict something using two variables, so multivariable regression. And what I thought I would do this week as I was looking through all of the figures that you gave me last week, Monday, was to base my lectures on the analysis of these projects. So although I might be choosing one particular data set to exemplify a particular idea, it doesn't mean that it's not relevant to one of the other projects. But these will all be things that I've seen some of the issues that you've confronted working on your projects. So we're going to tie together a bunch of final concepts on regression today. So the first example is from the Colorado Front Range precipitation data. There we have 56 weather stations, and we've got the average daily rainfall and the elevation. And people are interested in the relationship between elevation and precipitation. So here's a plot that shows elevation on the y-axis and average daily rainfall at each of those 56 weather stations on the x-axis. And so my question here is, if you're interested in this relationship, what's the natural variable that you would want to put on the y-axis as opposed to the x-axis? So this is something that you're all facing, is what variable do you want to plot on the y-axis compared to what variable do you want to plot on the x-axis? The x-axis is often called the independent variable, and that comes from experimental design, where you have the opportunity to modify and control what levels of the x variable you're going to be measuring, be setting, and then you measure the response in the y variable. But in general, we want to think about the variable that goes on the y-axis is the one that we want to see how does it depend on, or how does it respond to the variable on the x-axis. So what do you think? Yeah? Elevation should be on the x-axis because right, so you want to see what happens to rainfall at different elevations, basically, is what you're saying, right? And yes, in a way, you have more control over where you're placing these weather stations. But in particular, you're interested in how does rainfall change or depend on elevation. And so it makes sort of more sense to think about it this way, with rainfall on the y-axis and elevation on the x-axis. Okay? So when you're making your plots, think about what makes sense to be on your y-axis as opposed to your x-axis. The y-axis is the one that you're interested in seeing how it varies as a function of elevation. All right, so what do you think of those 2 points way out there at elevation above 10,000 feet? So I marked them in red, and I'm calling them influential observations because we might ask ourselves, how would the relationship between elevation and rainfall change without those 2 points? The reason why I picked those two is because both their x dimension, their elevation, and the rainfall are out of the regular range from the other observations. So if I were to do a density plot of elevation or a density plot of average daily rainfall in both of those dimensions, those two observations would be the largest ones. So it turns out that when we include those 2 points, the correlation's 0.34. And when we exclude those 2 points, the correlation drops to 0.14. So that's because if you can just sort of ignore those 2 red points up there and look at the remaining points, it doesn't really look like there's much of a linear association between the rest of those points. But by putting those 2 out there, away from the rest of the bulk of the data, then all of a sudden it starts looking like there's a relationship between the big blob and those 2 points way out there. Now it could be that those are really 2 legitimate points that you do want to include in your analysis, in which case you're happy that you are able to take measurements at that high of elevation and determine this relationship. And other times you say, well, you might say, well, maybe there's something wrong with those measurements, and you check to see whether it's based on too few data or there's some unusual circumstances. So maybe you find something wrong with them, or maybe you decide that you think that in fact there's they are different enough from the rest of the observations that you want to not include them when you're doing your analysis. So those are the kinds of questions you ask yourself when you see these kinds of influential observations. Here's data that I've just made up to make the point. On the left-hand side is my scatter plot of x on y, and I've got this one red point way high in the upper right corner. And the correlation between x and y is 0.66 when I include that red point. And when I drop the red point from the correlation calculation, it drops to 0.31. Notice that if I go ahead and fit a line through all the points, including the red one, and take a look at the residuals, the red point doesn't have an unusually large residual. It's not saying I've got a lousy fit. It's the size of its residual is not even the largest one. Here's the largest one down here at less than -2. So it's well within the realm of the size of the residuals for all of the other points. But because it's so far away from the rest of the bulk of the data, it's having a large impact on the correlation and on the fitting of the line. So the fact that the correlation drops by a half means that what happens to the slope of the line, if we have, I haven't given you the SD of y and the SD of x, but you can tell what's going to happen to the slope of the line when I include that red point and when I exclude the red point. So what happens to the slope of the line when I exclude the red point? Does it get steeper? Does it get less steep? By about how much? Yes? Without or with the red? With the red point, it's 0.66 times the SD of y times over the SD of x. Without it, it's only 0.31, right? So then it gets less steep, yeah. Right? So if I drop that red point, the line will decrease its slope by about a half. So we don't even need to know what the slope is. We already know the impact on the slope. Well, actually, that's not quite true. Sorry. Why is what I just said not really quite true? The SD of y and the SD of x will also change when I delete that red point, right? This is a large, slightly outlying observation, and so the SD of y and the SD of x will also decrease. And so we don't exactly know what's going to happen to the slope. But chances are it will decrease quite significantly. Here's another another kind of influential point. In this case, with the red point, which is over here. So before we even compare the correlations, notice something about the red point has an x-coordinate and a y-coordinate. In terms of the x-coordinate, is it a large observation? Yes, right? It's all the way out here around 9, and the rest of the data, the largest one is about 3. How about in terms of the y-coordinate? Is it a large observation? No, it's right smack in the lower quartile of the y values. So its y value is not unusually large, but its x value is. So when we're thinking about outliers with scatter plots, we have to be careful in that something that's not an outlier in terms of the y values, but is an outlier in the x values, that can be an outlier for our scatter plot. What happens with that point is that the correlation is only 0.06. It says there's roughly no linear association between these, but without it, the correlation's 0.68. So you can see that the black line is the line that's fit without the red point. And the red line is the line that's fit with the red point. So there are many ways that individual observations can influence the correlation and the fit of a line to a scatter plot. So this is quite different from the other. Here's one where x and z, where the point xz is far from the cluster or the cloud of the other points. Is this point, if you only look at its x value, is it unusually small or unusually large? No. If you look at its z value, is it unusually large or unusually small? Not really, compared to the others. So again, the correlation with that point is 0.42, and without that point is 0.68. So that point, if we only look at its x value, it's not an outlier. If we only look at its z value, it's not an outlier. But when we look at it plotted in our scatter plot, then the combination in terms of the relationship between x and z is an outlier. So what do you think the residual might look like for this point? Positive, negative, large, not large? The residual is the difference between the actual value of z and the fitted value, which would be on the line. So the same x value, but it's the point on the line right above that x value. Is the residual positive? Yes. Is it large? Yeah, there it is. So here's a case where when you do a residual plot, a value does come out and say, oh, I should take a look at that. So notice that it's not always the case that we'll have large residuals when there's something that we need to further investigate. So it is good to look at residual plots, but residual plots don't tell us everything. We also need to look at the original scatter plot. Okay, what to do with these points? We've discussed this already. You investigate whether there are errors in the recording or the measuring for these particular points. You investigate whether the conditions under which you took these measurements are different from the conditions under which you took the measurements for the other points. You may want to discard the observation if you found that there are errors in it, or correct it. Or you may want to simply keep the observation because it does improve the fit and you believe that it actually is a valid point in your scatter plot and, in fact, gives you more information and improves your fit. That you're lucky to have a measurement out there as opposed to this is really a whole different can of worms. I don't want this to be part of the relationship. Okay, here's another little scenario. In the wireless geolocation, the distance is from the device emitting the signal to the access point that's receiving the signal. The signal strength is detected at the access point, and we've discovered that the limit of the signal strength is minus 92. Remember, they're all negative values, and the smaller the value, the the weaker the signal, and minus 92 is the minimum value. And when we ask what's the relationship between signal strength and distance from the access point, which variable do we want to put on the y-axis versus the x-axis? So what goes on the y-axis? Signal strength. Good. So here's a plot which all of you who are working with the wireless data have already made. Those of you who have not seen this, do you see anything unusual about this plot between signal strength and distance from the access point? It doesn't look linear. That's right. It looks like there's some curvature. Yes? It could be that you want to transform it with a log. Yes? What else is strange? It's much wider at the bottom than the top. That's right. And in particular way at the bottom, you've got a line of minus 92s. So that's basically the minus 92 is at the point where you can no longer, you're at the limit of the equipment that's measuring the signal. So if you're looking for the relationship between signal strength and distance, does it make sense to include the minus 92s in the plot? Probably not. Okay? Because that's beyond the what the access point can actually detect. That's the minus 92. It says, well, it could be that or lower. So if we're looking for that relationship, that whole line of values at minus 92, one is it could, as we've seen already, that could really impact the relationship that you fit. And the other is you'd look into it and say, well, is it appropriate to include these points? And when you find that it reaches the threshold of what the machine can actually read out and detect, you think, no, probably not. Okay, mercury levels in fish. We're looking at the mercury level, and in this particular case, I'm just looking at the length of the fish and ask what's the relationship between these two. Again, which variable do we plot on the y-axis? Would it be the mercury level or the length of the fish? Mercury, that's the thing that we're wanting to see. How does it depend on the length of the fish? Here's one of these plots. Those of you who are working with mercury, what have you discovered about this? What's the issue that you're grappling with when you're dealing with these data? Yeah, a problem with this scatter plot. I know some of you talked about it. So let's take a look at, remember how what we're thinking about is trying to look at a particular length and then predicting mercury or estimating mercury based on length. So we can look at a vertical strip at 30 and a vertical strip at 50. So notice that the points within this vertical strip, compare them to the points in that vertical strip. Do they have the same variation? Do the fish that vary the mercury levels around that particular length, is it the same for length 30 as it is for length 50? Yes?
No, you could have a pretty long fish and see very different mercury levels in it, all real high.
Right. That's right. So that's what you see here, right? You see the red dot there is higher. So the average is higher, but the variability, like you're saying, is the SD of the mercury just within this strip at 50 is 0.84 compared to the SD of mercury within this strip is only 0.32. So the standard deviation, the variability, the spread is growing as we look at as the length of the fish grows. How does this affect the regression line? It actually, as long as it funnels, and it's not quite the case here, so as long as it funnels sort of evenly, meaning the variability or the spread is growing with the length, around a line, which it's almost like that here, then the line still is a pretty good fit to the data. The problem gets to be when you start to say how accurate is your estimate. The root mean square error of the regression line is one value that you're applying whether you have a 30 length fish or a 50 length fish, and then you can see how that's not that accurate. So you have to be really careful when you're making confidence intervals for lengths of fish if you've got this kind of funneling. Okay, so the spread about the regression line increases. So I, again, have made fabricated data, which makes it much clearer what's going on. Here is just x and y, and we see how the scatter points near 0, between 0 and 1, are really close to the line. And as we increase x, we get a larger spread. So to the point we're out here by 4, the spread's quite large. So I've created the data so that the spread exactly depends on the size of x. When we fit our line, this is the kind of residual plot we get over here on the right. Notice how it does look like the residuals are sort of evenly divided between the positive and the negative. There's not any one particularly large outlier I need to worry about. But again, you see the funneling going across the page. Okay? So that says again that the regression line is probably a good estimate no matter where you are with the x's, but the error that you would attach to your estimate if you're using the regression line, you have to be really careful with. That's called heteroscedasticity, meaning the variance is not homoscedastic. It's not the same across the x's. It varies with the x's. There are ways to handle this, which we're not going to get into now in this class. Next concept, the behavioral risk survey. Two of the variables that people are interested in is physical health, which is, I believe, the number of days you're sick in the past 30 days, and your weight. And what's the relationship between physical health and weight? So here's a plot. I've made a hex bin plot because they've got 20,000 observations. And when you make a scatter plot, there's a huge amount of overplotting. And so what you can see is that most people weigh in the 100 to 200 range, and we're not sick any days or missed work or whatever because of illness any days in this 1 month period. The correlation between the two is really weak, 0.05. Okay? Now we could actually compute the average the average weight by state and the average number of days that in a particular state where the average number of days sick. And when we do that, we get a correlation of minus 0.28. This is called ecological correlation. Ecological correlation is, and this is relevant to the election people as well. Ecological correlation is a correlation between averages or between rates as opposed to individual measurements. So here you're taking a correlation on 50 points between the average weight in that state and the average day sick in that state. And you have to be really careful when you do this, because this is looking at the relationship between averages, not actually the relationship between weight and days sick. And it's often the case that correlation between averages or weights tends to be stronger than the correlation based on the actual individuals. You also might want to look at this and say, well, is this really, are there points that I'd want to investigate that are affecting the correlation? But that's not the message that I want to get across with this particular plot. It's simply the difference between looking at a relationship based on individuals and looking at the relationship based on an aggregate of individuals in these groups, which are states. So it's not that it's not valid to do this. It's fine to do this. You just have to be really careful when you do it, as to be aware of the potential pitfalls. So ecological correlation tends to overstate the strength of an association. Use it with caution. Sometimes you have no choice. Those people who are doing the election, your data is aggregated at the county level or the precinct level. There's no way you're going to find out what an individual person did in terms of who they voted for or not. That's private. The only way people get at that kind of information is through exit polls, when they say, so who did you vote for? But the actual ballot itself is secret, and so you can't see how an individual varies according to their demographics, for example. You can only look at that at an aggregate level. I think I had one more point. And so we also have to be careful how we interpret, if we fit lines through data like this, we have to be really careful as to how we interpret the coefficients, and we'll get to that next. Right next. Okay. So back to them, moving around to lots of different examples. Back to the fish example. If we look at the coefficient, let's take a look at the coefficient if we actually fit a line to try and predict mercury based on the length of the fish. So to get the slope, we only need the three pieces of information: the standard deviation in mercury, the standard deviation in length, and the correlation between mercury and length. We know that the slope is R, the correlation, times the SD of mercury, divided by the SD of the length of the fish. In this particular case, it's 0.058. So then the question is, well, what does that mean? How do I interpret the 0.058? Unfortunately, you guys don't know what the units are of this stuff, right? Or we don't have very much information about these data. You guys don't really know what they are, right? For the length.
It doesn't say.
Yeah.
We say
I think inches seems hard to believe, right? Are those fish really that long?
48, yeah, I don't know. It's a large enough mouth, so.
48 is like 4 feet long. Is that? I would think centimeters would be, I said inches also here, but I think it must be, a 4 foot long fish is pretty long. If we go back to look at here we go. Some are 60, that's as long as I am tall. I don't know if largemouth bass get to be that big. Do you know? Does anybody here know? I would think maybe it's centimeters, and that would be more like 2.5 feet long, right? Or 2 feet. Okay, so, sorry, here we are. So what does a 0.058 mean? And the reason why I was asking in terms of what are the units, it's, if we take a look at this, it says for every, so I have this in terms of inches, but I think centimeters makes more sense. For every increase in 1 centimeter in the fish's length, there is on average an increase in the mercury level of how did I get that? That's a mistake. It should be 0.058. I don't know where the 0.65 came from. So for every increase in a centimeter in length, there's an increase. You can expect that the fish will have an increase of 0.058 in terms of mercury level. Another way to think about it is in terms of the slope is R times the SD of Y divided by the SD of X. So the SD of mercury level divided by the SD of the length of the fish. And that says that for every increase in length that's 1 SD of length, you can expect the mercury level on average to increase by R times 1 SD of mercury. So that's how we interpret the slope. That doesn't mean that, and this is relevant to, I think, just about all the people dealing with scatter plots and fitting lines to data. I don't think, do we have any experimental data here? Oh yes, the wireless data, that's experimental, right? There you've actually gone around and you know the location and then you measure the signal strength. So you're one example where you actually have the case where the X's are determined by the investigators. In just about all the others, your X and Y variables are completely observational. So you are observing that longer fish tend to have more mercury in them. You have to be really careful about the difference between association and causation. So we are measuring the correlation between these two variables, length and the level of the mercury. The scientists didn't conduct an experiment where they raised the fish and they gave them specific different levels of mercury to consume or digest, and then they measured the amount of mercury in the fish. They caught or trapped fish and took those measurements. And so we have to be really careful about how we interpret what it means to say 1 inch or 1 centimeter more in length corresponds to a 0.058 increase in the mercury level. Okay? So it's saying when I look at fish that are 35 centimeters long versus I look at fish that are 36 centimeters long, that on average the 36 centimeter long fish will have 0.058 more mercury in it. It's not that if the fish grows another centimeter in length that you can say that this predictive model happens. And that's because of the fact that this is not an experiment, it's an observational study. Okay? All right. Just to continue with the mercury data, but this is something that's relevant to many of you. So when we're looking at when we're fitting a model of mercury on length, and we get out the intercept minus 1.13 and the slope 0.058, and there's an error attached to that. So you've seen how the length is to compute the estimates for the coefficient. That's based on lots of averaging. The correlation itself is an average of the product of standard units. And so inside of this is a complex average. And that average has a standard error, which is 0.005. And what often people want to test when they're looking at this is whether they really need to fit a line at all or not. And that's essentially testing a hypothesis as to whether or not the coefficient is 0 or not, whether the slope of the line is 0 or not. And so R gives you that test automatically. Sometimes you want to look at it and you care about it, other times you don't. We'll talk more about this on Wednesday, but just for this particular case, we look at the size of the 0.058, the slope, the estimated slope, to its error, 0.005. We see how far away is 0.058 from 0, which is our hypothesized value, that the slope's really 0. We don't need to fit a line. And we see that it's 11 standard units away, and we can compute p-values. Well, what's the chance we would wind up with a slope as large as 0.058 or larger, and when the slope's really 0? And we see that the probability of that is astronomically tiny. And so that says we would reject the hypothesis that the slope's 0. This can be very handy, especially handy if you're not sure, if you've got a very weak relationship and you're not sure whether you should be bothering to fit a line at all. You have to be careful. Obviously, it's working under the assumption that the linear association is the right association to be fitting. So just to back up a little bit, recall that the intercept is y bar minus the estimated coefficient, the slope, times x bar. So if the slope is 0, then the intercept is just y bar. And so that's essentially testing two different models, right? It's saying, it's testing whether or not the model that just says, my best predictor for the y value is y bar, no matter what x is. So that's a very simple model. It says essentially that there's not a meaningful relationship between the x and the y, and your best, you might as well just predict y using the average. That's the hypothesis that b equals 0, that the slope is 0. So that's what's going on when you do this hypothesis test on the previous page. It's sort of saying, is that slope, I'm testing whether that slope's 0, which says basically I'm just going to fit the mean to my data. And I have no extra information with x. So that's a hypothesis test that's going on there. Okay, let's take a look at the traffic data now. There are two variables of interest. We're just going to look at one lane of traffic. Flow is the number of vehicles that pass over a loop embedded in the freeway in a 5-minute period. And occupancy is the proportion of time that there was a vehicle on top of that loop in this same 5-minute interval. So we've got pairs of flow and occupancy. And we want to look at the relationship between flow and occupancy. And those of you who are working on traffic all got these rather interesting plots where it looks very linear and then there's some kind of degradation. There are lots of things you can do, and and I want to just show you something that's beyond fitting lines to data. So it's fine to try and fit a line to the earlier part of the data and see what that relationship is. Others of you have said, we've talked about possibly fitting a curve to the data. And so I want to show you how you might do that. So notice that when we get something that looks nonlinear, up to this point we've tried to have a transformation that transforms the relationship into one that's linear. Taking square roots, taking logs, something like that. None of those transformations are going to work in this particular situation. So what we can do is same idea as before, where we can look at a fixed little bandwidth of occupancy, look at flow, take the average, and have all these averages as we move across the page. And then rather than fitting a single line to all the averages, we fit a curve, a smooth curve without specifying what actual functional form it has. We just want it to be smooth. Basically, what I'm fitting here is parabolas of degree, or polynomials of degree 3. So similar to what you can do when you create a density plot of one variable, you notice that the bandwidth is, as you shrink the bandwidth, you see more of the data, and it gets more jiggly. And as the bandwidth increases, you wind up simply seeing the underlying normal that you're using to smooth. Same things here. You can adjust the bandwidth, so to speak. And the blue one is the default value. And notice that it's the smallest value. And notice how it fits the data way out here a little too closely. It's going through, it's really jaggedy. So we can adjust it. The green is where I've adjusted it so far that it deviates. It doesn't pick up the main structure on the left-hand side, but it's nice and smooth. And the red is where it keeps the sort of very linear relationship, and then it sort of breaks down after that point. And so here are 3 different ways of doing local smoothing for 3 different bandwidths. And again, it's an art to pick those, or there are other techniques which we won't get into in this class for how do you pick that bandwidth. So essentially it's saying I don't actually really, I'm not going to know what the actual functional form is of this curve that I'm fitting in terms of a nice function like x squared or some kind of polynomial or something like that. Instead, what we're going to get out is one of these smooth curves that we can still use. It doesn't, it becomes, if you're looking for a model that's got a nice form to it, this kind of smoothing doesn't give you that. But on the other hand, you can fit the data really well if you think that that nice model isn't worth trying to pursue or isn't actually pursuable. Okay? Yes, sorry.
How come the smaller the 0.0001
Mm-hmm.
is the green?
Yeah.
That it's more smooth is that number is smaller? Like this result that you see.
So the red one is so the smallest one's it's not in order, unfortunately. The blue one's the smallest. So it's the default, and I put it first, but I realized afterwards that it should be on the bottom. It's the absolute smallest. Is that the point of confusion? So it's much smaller than 0.00000001. It's actually 1 to the minus 12, I think, or something like that. Right. Any other questions? So here, I've just put this up here for you if any of you are interested in fitting these kinds of curves to your data. The Fields package, which some of you have already gotten quite familiar with those thin plate splines, which is essentially doing the same thing, but in 3 dimensions, where you've got your x, y, and your z is your precipitation. That's the same thing that's going on here, except you just have x, and then you're fitting a curve, now just a simple curve in the y dimension to your data. So anyway, that's how you do it. And so the last thing I want to say is for today, we've seen a bunch of different concepts in terms of variance in your data changing with the size of x, influential and outlying observations and what to deal with them, ecological regression and how to be careful with it, how do you interpret a coefficient, how do you fit something other than a line. But basically, I want to make sure that when you're doing your analysis that you just step back and ask yourself, okay, what am I doing? What do I see here in the statistics? If there's summary statistics I'm calculating, a plot I'm making, a hypothesis test I'm conducting, a confidence interval for an underlying population, the regression line or smooth curve that I'm fitting to my data. What am I doing? How is it helping me answer my overall question? What do I see in my plot that's leading me to make a statement about some relationship related to the question I'm trying to answer? So continue to sort of try and see something in the plot you're making, interpret the statistics you're creating, or the coefficients, or the relationship between 2 variables or 3 variables. Interpret it in the context of the question and see what the data are telling you. Don't simply report the statistics and say, here they are, blah, blah, blah. The mean's this, the median's this, the interquartile range is this. Say something, what does that tell you about the distribution of that variable? And how does that reflect on the question you're trying to answer? And that's it, unless people have any questions. So on Wednesday, we're going to look at multivariate, 2 variables to predict 1.